So recurrent neural networks are different from feed-forward networks in that they allow cycles in the computation graph. So in all the problems that we look at, each cycle has a delay, so that units may take as input a value computed from their own output at an earlier step in the computation. So this allows the recurrent neural network to have what's called a memory. Inputs received at earlier time steps affect the recurrent neural network response to the current input. So this is the main difference between RNNs and feed-forward network that we've seen so far. So RNNs can also be used to perform more general computations without the memory, essentially, and to model real neural systems, many of which contain cyclic connections. So in this class, we focus on using RNNs to analyze sequential data, where we assume that a new input vector x sub t arrives at each time step. Now, RNN can be compared to hidden Markov models or dynamic Bayesian networks or Kalman filters. Okay, so similar to all these models, RNNs make a Markov assumption, which essentially is that the hidden state ZT of the network is enough to capture the information from all the previous inputs. This is the Markov assumption, which is the foundation for Markov models and dynamic Bayesian networks. So you don't need to go further than ZT to know what happened earlier in the network. All you need to know is the hidden state ZT. In addition, if we assume that we describe the RNN's update process for the hidden state by the equation saying that ZT is a function of ZT minus 1 and the new input xt. Once we train this function, it will represent a time homogeneous process, which means effectively universally that the dynamic presented by that model will hold for all time steps after that. So RNNs then add expressive power compared to simple feed-forward networks. Just as convolution neural networks that we've seen for image processing also add expressive power by their ability to split the input into local areas and identify what's in each local area of the picture. RNNs also add expressive power by giving you this memory component for each unit. If you try to analyze sequential data or time series data using a feed-forward network, the fixed size of the input layer would force the network to examine only a finite length window of the data, right? Because you have to cut the data at some point. So for example, let's say you're looking at the sequence of stock prices. Essentially it's an infinite sequence because you don't know what happened in the future. So you're going to have to fix a window size. You're going to say, well, I'm just going to limit myself to the previous 10 days, for example, as input to try to predict what happens on the next day. With RNN, you don't have to do that. because the RNN can just you input one time step, and then every information that's contained in that time step will go into the memory of the units, and then will be reflected in future steps after that. Now, training a basic RNN, like we said, will have an input layer X. We'll have a hidden layer, we call it Z, and this hidden layer has this characteristic of having a recurrent connection, and we'll have an output layer Y. So let's look at how the architecture of the RNN looks like before we move forward. So this is the RNN. So you have X, you have the hidden layer Z, and you have the output vector Y. Now, if you unroll this over, for example, 3 time steps, then you can say that X1 here, that's your very first input at time step 1, hidden layer Z1, and gives you output Y1. Now, that output Y1, you can feed it with the new input X2, or you can compare it to the true value at Y1 and calculate a loss. We can do many things with it. Then the hidden layer Z1 will have a weight to impact the next hidden layer Z2 and so on. The next value for the hidden layer at time T2 and so on. So X1, X2, X3, all of these, we call them unrolled because there are across time steps. 3 time steps in that case. Note that the weights are shared across all time steps. Okay, so all these weights are shared across all time steps. So if we go back to our equations here, so we say that ZT is a function of the hidden layer state at t minus 1 and the input at time t, which is going to be some activation function times the weight times zt minus 1 plus the weight times x, the new input at time t. Okay, and then the output y hat at time t will be some activation function of the weights times the hidden units zt. So these equations describe essentially the recurrent neural network training process here. Now, our loss functions, we will define different loss functions that will depend on the specific problem we're interested in. For example, if you're doing a time series problem and you're interested in the loss at each time period, the error at each time period, then you will compare y1 to y hat 1, y2 to y hat 2, and so on. If you're doing text translation, you will see that we will construct a loss function that is different. If we're interested in classification, say sentiment analysis, for example, where we have a sentence or a paragraph typed by a user, and you want to classify the sentiment in that paragraph as positive or negative. So in that case, we're only interested in that classification output. So the loss function will depend on the specific application that we're developing. Of course, in these equations, remember that gz and gy here are the activation functions for the hidden layer and the output layer. And as usual, we will assume that we have an extra dummy input for each unit as well to represent the bias like we did in the feed-forward network. So now, given a sequence of input vector x1 all the way to xt and the observed output y1 to yt, So, and we unroll the network in t time steps, like we saw here. Then it's easy to calculate the gradients to train the weights, and exactly like we did with the feed-forward network. The only difference is that the sharing of weights across layers makes the gradient complication a little bit more complicated. So this is the equation we're going to use to calculate the gradient for the hidden unit ZT. But you can see that we did not include the equation for the loss function because it is just it's going to be much bigger, but it's the same process as we did with feed-forward method. Just notice two things about this equation. First is that the gradient expression is recursive, which means that the contribution to the gradient from time step t is calculated using the contribution from time step t minus 1. So if we order the calculations the right way, then the total runtime for computing the gradient will be linear in the size of the network. So this algorithm is called essentially backpropagation through time because we start at time step t and then we go backward, calculate the gradient at t minus 1. The second thing you need to note is that if we iterate the recursive calculation, we see that the gradient at the end of the sequence, big T, will include terms proportional to all the weights from t equal 1 all the way to the end of the sequence. So, which means that we will also have the same problem of vanishing gradients because if your sequence is very long, so for example, let's say you're analyzing a text that's an entire page, of text, the longer the sequence is, the higher the risk of the network forgetting what happened earlier in the sequence, which is essentially the vanishing gradient problem that we faced as well with deep neural network if we make the network too deep. In addition, if the weights are W are bigger than 1, then we might experience the exploding gradient problem. Okay, so that's essentially the exact opposite of the vanishing gradient problem we experienced earlier. So we're going to discuss some ways to try to deal with these two problems in the next video.